All right, so I'm guessing you're all familiar with standard regular expressions, and maybe you know that with just a few constructs, characters, concatenation, disjunction, and iteration, you strike a very convenient balance between expressivity and simplicity. And this has been studied since the 50s, so we know that from this simplicity, we can get some very efficient matching algorithms. One example is called NFA simulation, and basically what you do is that you construct a non-deterministic finite automaton for your regex, like this one on the right, and then you look for a path in this NFA that corresponds to your string. And the good news is that all of that can be done with a linear complexity, and when I say linear, I mean linear in both the size of the regex and the size of the string. However, despite all of this previous established work, you might be surprised to learn that today most regex engines do not have linear complexity. Instead, they rely on a backtracking algorithm that has an exponential complexity in the size of the string. And this is a default in many programming languages and libraries. And this, of course, can have serious consequences. One of them is called RDOS, regex denial of service. Basically, if your application spends its time trying to match a regex, it can bring it down. And this has happened in the past, and a lot of applications are vulnerable. So why are we not using those nice linear algorithms? Well, one of the main reasons is that regexes have changed a lot. We no longer have just the simple features from above. We also have many new features like character classes, anchors, capture groups, and so on. Now, some of these features, the one in green, we know that we can match them linearly. We have linear algorithms that support them. On the other hand, back references, we know that they make matching NP-hard, so we don't have any linear algorithms for them. But in between, for lookarounds, look-aheads, and look-behinds, we don't really have such complexity results, nor we have linear algorithms. Okay. So if you want to avoid RDOS today, you can try to have a linear engine and focus only on the green features. And so this is what happens by default in Rust and Go and some libraries like Re2. And if you already have a big language with all of the complex features, you can have a backtracking engine for the whole language. And whenever you don't have any back references or lookarounds, you can switch to a linear engine. This is what happens for JavaScript in V8. There is an optional linear engine for JavaScript regexes. However, all of these different linear engines, they all need to be slightly different because different regex languages have different semantics. For instance, capture groups have very special semantics in JavaScript that we will see later on. Some look-behinds are valid in some languages, but not valid in other languages. And we will see that even something as simple as a star is different in JavaScript than it is in any other language. So in our work, we study the consequences of the JavaScript semantic choices. They have an effect on the matching algorithms and their complexity. And we find that, surprisingly, some of the JavaScript semantic choices are actually great if we want to match things linearly. To sum everything up, we have a lot of features, and for a lot of them, we know that we have linear engines in most languages. So all of these features we know how to match linearly. But we also know that the JavaScript regex semantics is really weird. And because of that weirdness, many standard algorithms are not actually applicable. And what we found is that in the linear engine of V8, for different features, we found some semantic bugs or incorrect complexity, nonlinear complexity for various features because of JavaScript semantics. And so the first thing we do is that we designed a new algorithm and show that despite the weirdness, we can still match a very large subset of JavaScript regexes in linear time. But then we go even further, and we show that thanks to this weirdness of JavaScript semantics, we can actually match even more features linearly than we can in other languages. And we show linear algorithms for lookarounds in JavaScript. As a bonus, one of our algorithm restriction can also be applied to other languages, but if you want the full thing, you really want the JavaScript semantics. Okay. Today I will present two of our algorithms, and the first one is about the JavaScript star, which I said is different than in other languages. But before I can really go into these details, I want to talk to you about priority in modern regex languages. In those modern regex languages, whenever you try to match a regex on a string, you not only want a Boolean telling you if there is a match or not, you're also interested in where does the match start and end. So for instance, if you're trying to match the regex D or B on the string ABCD, an engine should tell you that yes, there is a match, and also that there is a match on the letter B. If you try to match A or AB, you might expect that the longest match is going to be returned, but that's not the case. It's going to be a match only on A. And if you try to match AB star, you might expect it could be just A or AB, but it's going to match ABB. So in all of these ambiguous cases, where the regex could be matched in different ways, we need to find a way to specify which match we want to return exactly. And so all of these languages, they follow some simple priority rules. For instance, the first match in the string has a priority, which explains the first example. For the second one, whenever you have a disjunction, the first branch, the left branch, has a priority. And finally, whenever you have a quantifier, like just a star, you try to do as many iterations of that star as possible. So this is all fine, but that last rule can create some issues. Because what happens when we have a regex that can match the empty string in a star, for instance, epsilon star? We don't want to define the behaviors of this as doing as many repetitions as possible, because then it would just do an infinite loop, and that's not how we want to define the behaviors of this. And so whenever we define a regex language, the semantics of the quantifiers, they need to find a way to prevent infinite repetition. And what we found is that there are actually two ways to do so. One that is used in any language that we know except JavaScript, and one that is used in JavaScript. So in most languages, we are going to say that epsilon loops are forbidden, and I'm going to explain this on an example. However, in JavaScript, we're going to say that entire iterations of the star cannot match the empty string. Let's find an example where this is different. If I try to match this regex, A or epsilon or B star on AB, in most languages, I'm going to go into my star and I'm going to match A. Then I'm going to match epsilon because this is the branch on the left of the disjunction, so it has priority. Okay. Next, I'm going to try and do another iteration of my star. So this time I have no choice but to match epsilon because I already read A. And at this point, I realize that I've done an epsilon loop. I've gone back from a point in the regex to the same point in the regex without reading any character in the string. And so I cannot do this. I conclude that I can only do one single iteration, and my match is only on A. However, on JavaScript, of course, it's going to be different. We can do the same first iteration, and that iteration did read a character. And then we can do another iteration, and this time we are allowed to match epsilon and then B, and it is still a non-empty iteration, and so the result in JavaScript is actually to match AB. The problem with this semantics is that all of the linear algorithms that we know, they do not implement the JavaScript semantics, they implement the other one, of course. Let's look at NFA simulation, for instance. So we build an NFA for that same regex that we just saw before. It's a special NFA because I put some edges in bold to indicate priority, and then the algorithm is trying to find the top priority path in that NFA. As we do explore paths in our algorithm, we always check that we don't visit the same configuration twice. And by configuration, I mean the same regex state with the same input string position. And these checks, we really don't want to mess with them because these checks are what makes the algorithm linear, so we don't want to remove any of them. But of course, the issue is that it's going to discard epsilon loops, and so this cannot find the top priority path of the JavaScript semantics. Because if I do my first iteration and I read an A, if I try to do a second one, I will go back to S3 without reading any character, and so I cannot find the JavaScript top priority path. Now, how can we fix this? Well, one way to look at it is to focus on state S5. So in JavaScript, in S5, there should be two behaviors. Either I read a character in my last iteration, in which case I should be allowed to go back to S0, or I did not read any character, and then I should not be allowed to go to S0. So it's a bit weird to have those two behaviors for a single state, so what we suggest is a different NFA construction in which we have two copies of the NFA. I added some square nodes, begin and end, to indicate the beginning and the end of a loop. And now we have all the states on the left that represent states that are allowed to exit the star, and on the right you are not allowed to exit the star because of the JavaScript semantics. So of course, every time we enter a new loop, when we go through begin, we just move to the right, and whenever we read a character, we can move back to the left. And this construction is enough to actually match the JavaScript semantics because when we do our first iteration, we read an A, and then if we try to do a loop, we will go back this time to T3, which is not the same as S3, and so we can continue with exploring our path, and we will find the JavaScript match. So just with this new construction, we restored the correctness for the JavaScript star. it's still a linear algorithm, and we only need a single copy. And we also implemented this in the linear engine of V8 because it was using the previous algorithm, and so it was actually incorrect in some edge cases. Okay. Next, I would like to talk about another feature, a feature that we don't usually match linearly. I'm talking about lookarounds with capture groups inside of them. So let's try and see what this is exactly. A lookaround is a way to put a condition inside your regex. If I try to match A look ahead B, I'm trying to match any letter A that is followed by a B. Note that B is not part of the match, only A is, but I only want to match A when there is a B after. In this other example, I'm trying to match a sequence of numbers that is followed by the following letters. And so, of course, it will match 27 in June 27th, but it cannot match anything in PLDI24. Okay. Then I also talked about capture groups, and while lookarounds we usually don't know how to match linearly, capture groups we do know, and we do have linear algorithms for them. Basically, the idea is that you not only want the positions at which the match starts and ends, you also want the positions for each sub-expression inside parentheses. You want to know which part of the string they last matched. So if I'm trying to match A, B or C and then D on this string, an engine should return that not only I have a match on the substring ACD, but also that my parentheses, my expression inside parentheses, matched exactly the letter C. And of course, JavaScript being JavaScript, capture groups are different in JavaScript. And so there is this weird property, and I don't know why it is this way, that at each iteration of the star, you forget about the value of all the capture groups that are inside that star. And so basically on that example, you would do a first iteration of the star where you go through the left branch to match A, and doing so you define a value for the capture group inside of the star. But as you do a second iteration, you forget entirely about the value of that capture group, and so in the final result, the value for that inner capture group is just undefined. Okay. So how can we match lookarounds in linear time? Well, we design an algorithm that relies on two key ideas. The first key idea is that we found a way in linear time to pre-compute every position at which each lookaround will hold in a string. Basically, we need to reverse a regex for lookaheads, but I'm not going to go too much into details today. So yeah, we can compute this table, and so this is the first step of our algorithm. We're going to, let's say for instance, I have a regex with one lookahead, A or B. Then I can compute this table, which tells me that A or B is true at the first three positions, but of course at the end it's not true anymore. Okay. Now that we have this table, it's very easy to match the main expression, because I can just transform this lookahead into a special node that I call L here, that is going to check the table to see if the lookaround holds or not. So for instance, if I were to execute this regex, I would say that in the first two iterations, I can check the table to see that it is in fact valid, and I can go on in my path. And if I tried to do a third iteration of the star, it would tell me that no, I cannot do it at this moment because the lookahead does not hold. However, even though we can match the main expression this way, we still have an issue because lookarounds can also define capture groups. And my table tells me when lookarounds are true, but it does not tell me what are the capture groups defined inside the lookaround. And this is where the JavaScript semantics comes to the rescue, because we found that one consequence of capture reset is that every capture group that is defined inside a lookaround can only ever be defined in the last iteration, in the last time we used that lookaround. And what this means is that we can reconstruct all of the groups defined inside lookarounds after we have matched the main expression. And we can do so by matching each lookaround only once from the last position where we used them. So in my example, I last used the lookahead at the position 3, and so I can just build an NFA for the inside of the lookaround and try to match that thing after matching the whole expression, and I will get my missing capture groups. The whole algorithm is linear because we are allowed to do this only once per lookaround, and we can do this only once per lookaround thanks to the JavaScript semantics. In our paper, we have many more algorithms for many more features in which we either fixed the standard algorithms or we fixed the complexities that we found in the linear engine of V8, and we added support for unsupported features like lookarounds with capture groups in them. We still have an open question though, in the particular case where the plus is both nullable, it can match the empty string, and also it is lazy. We don't know if we can match this linearly in the size of the regex. In all of the cases, if you're not lazy, we can match it linearly. If you're not nullable, we can match it linearly. But in that case, we're still not sure. We implemented all of these algorithms in our own JavaScript regex engine that is called regex. And some of them we also implemented in the linear engine of V8, meaning that, for instance, if you use Google Chrome, you already have our algorithms on your computer and you have the very first deployed linear engine that supports look behinds. We could check experimentally that if we increase the size of the regex or the size of the string, all our algorithms increase the matching time linearly, which is exactly what we wanted. And so we learned a lot about how to match JavaScript regexes linearly. We know that despite all of the weirdness of JavaScript semantics, we can still match a very large subset of them in linear time. And we learned that we can even match lookarounds with groups in JavaScript. I would also say that we learned some important things about modern regex semantics and how to design a regex language. We learned that it's really important to consider the interplay between different features, like the interplay between capture groups and lookarounds. It's also important to consider the regex size complexity because much of the inaccuracies that we found in other engines were due to that. We also found that some semantic design choices just make your life harder, and this is the case for the JavaScript star. Even though we found a linear algorithms, it's just more complex than in the standard case. But more importantly, we learned that some semantic choices, like capture resets, is actually a great thing if you want to match more features linearly. And if we use all of that, we should be able to have regex languages that are expressive because they have lookarounds with capture groups in them, but also that are safe against redos because we have linear implementations. Thank you.
Okay, we have some time for questions, so please approach the mic and ask your question.
So it sounds like this is all just one big coincidence, that we have some guys who don't understand what regular expressions really are, so they go off and build some busted regular expression semantics. Then it comes along, it turns out that with this busted semantics, you can actually do a whole lot of other things better. So is there some purposeful way of doing this, applying this thing more generally, or do we just have to wait for weird things to happen and hope that not too many people are educated in programming languages when they build programming languages?
It's a good question and a good remark. So to cut some slack to the ones that design, the JavaScript semantics, I would say that they're not the only ones. I mean, people have been adding new features into modern regexes without ever asking what the complexity of this could be. And so they made some choices that are different, and it so happens that those choices are sometimes good. Yeah, I feel like if now we can try and identify which are the good choices, then hopefully it will be better in the future. I don't know if that answers your question. Or... Okay, yeah.
I know. So to what extent should we mangle the semantics of the things that we're working with to make them more efficiently implementable, I guess is a different question.
Okay, then, yeah. I don't think I've ever seen anyone complain, for instance, about things like capture reset. So I would feel like if you added capture reset in a new language, people wouldn't be mad about it. And in fact, there are so many people that are already using it, sometimes without knowing. I don't think it would be fair to change an existing language because maybe some regexes already depend on the previous behavior. But I don't feel like we are sacrificing much with that.
Well, the answer is we should do it.
Yeah, I believe so, yeah.
Okay,
Continuing that line, sorry. The first part is, let me just ask, there's been recent work actually and not so recent work on look-around processing at Poplar, for example, doing in linear time. How's that related to your work in this case?
Yeah, so if we look at our three-step algorithm, so there was this other paper at Poplar this year that also had an algorithm that basically corresponds to the two first steps of our algorithm. So in my understanding, there are no capture groups inside, but there is a whole formalization of how that works and the semantics of all that. So yeah, it seems like for this first ID, we just had the same ID at the same time to reverse, and you get all of these positions that we get. I would say that I feel like it's also important to see this interplay with capture groups, because in modern languages you have capture groups, and so if we want that to actually fit into modern regex languages, to be able to match them together is nice.
So following on that one, so first of all, I would prefer personally if standard regular expressions were called regular expressions.
Mm-hmm.
And the second part is that it's possible actually that to get full syntax trees, not just capture groups, but nested
Yes.
syntax trees at arbitrary level. And you can do that at 1 to 10 gigabit per second. Exploiting that, you actually have very nice semantics.
Mm-hmm.
And that's from 2016,
Yeah.
Popple. And I'm just wondering actually why, it's the same question Martin actually asked, is why are we actually basically sufficiently destroying or not being aware of wonderful semantic properties that can be exploited for guaranteed linear time performance with very high sustained real-time throughput, streaming, fully streaming, and actually fixing things that are actually built to, are being broken from the beginning. So that's maybe a philosophical question, but so there is work out there.
Mm-hmm.
Actually, there's also mathematical theory. It says like you can always get the greedy parse, and is well defined what a greedy parse means. It seems to be neither the first of those two examples he gave, and they have nice closure properties that actually then mean that you can get very fast algorithms for these things. But that seems to be not very popular. People want to play with these backtracking algorithms, and then it's like, broken car, you prefer to actually fix a broken car than buying a new one that actually never gets broken. Mm-hmm. So what is going on here?
So there is some
in JavaScript in this case, yeah.
Yeah, there is some truth to that for sure, that we have just added blindly stuff without realizing what they meant. I would slightly disagree maybe with the fact that we're just working with a broken car, because once again, this consequence of capture reset, I feel like inadvertently we touch on some nice properties. So I wouldn't say that everything is broken in JavaScript. There are actually some nice things in it.
Not everything, I hope, is broken in.
Let's move to the next question.
Okay.
Sorry.
But we can discuss this more offline if you want.
So on the topic of adding more broken things to the JavaScript regex, the recent-ishly there was a Unicode properties, Unicode proposal and string properties.
Yes.
What do you think about the linearity, I guess, of the string properties? Question number one, and two. You mentioned, okay, maybe let's just stick to number one here.
So it's a very good question, because for instance, this algorithm in general is not streaming because we need to build the whole table before we do this thing. Okay. One restriction of it we do when we have only look-behinds without capture groups, and in that case we learn that we don't have to build the whole table in advance, and so we can really have a streaming algorithm that could be implemented in every streaming regular expression engine. So yes, streaming does add some constraints. We can't have everything that we have in that slide, but we can have some other nice algorithms that we also have in the paper.
Okay.
Okay. Yep. Let's thank our speaker again.